Welcome back to AI Playground with Abhinav. This is session 4 of Agentic AI series. Last session, we looked at different instances where an LLM invented artifacts that actually didn't exist, and it caused millions of dollars of losses for the big shot companies. And then we did a deep dive on the fix it required. We built the design, and today we bring it to life. But here is a twist nobody tells you. RAG isn't one thing, it's three, and each one is a different kind of detective working the same case. Now let's talk about Detective 1, which is a traditional RAG, the one we designed and the one we are going to build today. Now, when you ask a question, this detective it grabs the matching files, returns an answer. It is fast, cheap, and it is kind of brilliant for clean, direct questions. But hand this detective a case buried across five different files, and it freezes. Now, this brings us to Detective 2, which is the graph RAG. This one works with a string board. Every fact pinned up, red strings connecting who links to whom. It doesn't just search, it follows the connections. Now, now this is not theory. LinkedIn wired this into their support system, and their ticket resolution time it came down from 40 hours to 15 hours. Now the questions were same, but this detective was smarter. Now comes Detective 3, which is called Agentic RAG, the third flavor. I call it the seasoned investigator. Now it doesn't just fudge the results. It thinks, it uses tools, and it checks its own work. If the answer feels weak, it goes back out and takes again. Now Uber built exactly this kind of agentic RAG and they named it Genie. Now when they upgraded to agentic RAG, wrong advices dropped by 60%. So three detectives, three different cases they have built to solve. One question that matters is that which one do you hire and when? Now that's exactly what we are answering today. First, I'll show you how each detective thinks, then we build one live with the real code and real answers. And we close this with the tips that turns a demo into a production grade assistant. Now, if you are new here, hit subscribe now because this build continues into session 5 as well, and you will want it landing in your feed. Now, one thing before we go further, if you haven't watched session 1 through 3, this is going to hurt. Not because the code we are going to show or build today is complex, because the code will make perfect sense, but you still won't know why it works. The moment I say refund and return policy sit 0.96 apart in a vector space, you might go ahead and nod, but you will miss the entire reason how the retrieval works at all. You won't know why we overlap chunks or what k equals to 6 even means. And later, when your own system returns empty answers and the AI swears the information isn't there, you won't know where to look. So please, if you have not watched the previous series, hit a pause. I have pasted the playlist link below, and then we can come back to this video. So let's talk about the three flavors of RAG. And I was talking about detectives, right? So picture a detective who has been handed a case, and the detective's mission is always the same, right? Don't guess, have the evidences in place, but how our detective digs through that evidences. Now that's where the three styles split apart, and they get sharper and more distinct as we go further. Now let's look at the first one, the traditional RAG. Now this is the first detective. You ask a question, they walk straight to a kind of a filing cabinet, pull the right folders that look most relevant, skim through them, and they give you an answer. Now one trip to the cabinet, no second guessing. Now this is the one we discussed last time. Embed the question, grab the closest chunk, hand them to the model, and you are done. And you know what? It's brilliant for what it is. It is fast, it is cheap, it is kind of that simple. If someone asks, what is your refund window? That that detective nails it every time. But here is the catch. Give them a question that's hidden across five different folders, five different files, where no single page has the whole answer. And they freeze because they can only see what looks similar to the question. They can't connect all the dots. Now, here is where graph RAG, which is the second one, if you look on the screen right now, the middle one, this comes in handy. So, meet detective number two, the one with the string board. And I'm sure you would have seen it in every crime show or a crime movie. Photos pinned to a board, red string running between them. Now, this suspect worked at that company, right? That company was quietly bought by this other one. That's exactly the kind of relationship the graph RAG builds. Every fact becomes a dot. Every relationship becomes a line connecting them. Now, watch what happens. If you ask who ultimately profited when a company A collapsed. Now, this is a generic question, right? And you don't have a right answer for that. You cannot just look at one file, one source, and answer that because there might be a lot of relationships. Now, the first detective would just look for pages that says profit or company A. But this one, the RAG, the graph RAG, this one follows the string, and it can look like A was owned by B, and then B's biggest stakeholder or shareholder was C, and then C sold this company right before the crash. Now that's a multi-hop question, and graph RAG walks the connections to get there. And when your knowledge is all tangled together, this is where you want your graph RAGs to come into action. Now let's talk about the extreme right. And now I feel that this is the star of the show, the seasoned investigator. This one doesn't just fetch evidences. They think, they decide what to chase and when. They realize the first lead was a dead end, so they rephrase the question and try a new angle. They pick up the phone, they call a source, they will run a background check using real tools. Then they stop and then they ask themselves, is this answer actually going to help me? Or is it actually good enough? And if it is not, they go back out and dig again, start from scratch. They retrieve, they reason, they act, and in a loop until the case is genuinely closed. Now it's slower, it costs more, but it's the only one that can handle a messy, moving real world investigation. So, to summarize, three detectives, three very different ways to crack a case. The real question is, which one do you hire? And that's exactly the next slide. Now, what you see on the screen right now is a quick comparison. Now you have met all the three detectives, and here is a trap almost every team falls into. They are so impressed by the brilliant self correcting investigator on the extreme right that they put him on every single case, including the ones where someone just asks, a very basic question. And that's how you burn your entire budget solving a parking ticket. You must have seen so many newses. You must have seen so many updates, blog posts, LinkedIn posts, where you see the companies are exhausting their token limits and their AI budgets are kind of already spent within 3 to 4 years, so 3 to 4 months of the financial year. Now let's think of this scenario as a police chief. Now this police chief has three detectives. He has a very limited budget, a stack of cases. Now who gets assigned to what? Now this table is your hiring guide, row by row, which rag you should use. Look at the row one. How do these detectives work and how do they find information? The first works by resemblance, the traditional RAG. It simply states find me files that kind of look like this, and they use semantic search, which we looked at in the last session. We talked about 1536 dimensions, the vector space, pointing into the same direction and all that good stuff. Now, the second one in the middle, the graph one, it follows relationships. Find me who is connected to whom. So that is a kind of answer, it finds out. The third on the extreme right, it sends an agent into the field to pull from wherever the answer actually lives. It does an exhaustive search. Look at row 29 right now, multi-hop questions. Now, can they handle a multi-hop question or multi-hop case? This is the second kind of question you should be asking. The kind where the answer is buried across 5 files. Now, the similarity search, the first directive, traditional AI, traditional lag, it doesn't help here, right? But the other two, they are the real winners here. Now, real consequences of getting this wrong. LinkedIn's standard RAG handled single document and they handled it perfectly. The moment a support case needed information connected across multiple entries, it stalled. So they had to switch from traditional RAG to graph RAG. And like I mentioned earlier, the resolution time came down from 40 hours to 15 hours. They had to hire smarter detective. So they switched from traditional RAG to graph RAG. Now look at row 3. Do they check their own work? Now only the agent catches his own mistakes and goes back out. The first two hand you their answers and they just simply walk away. Right or wrong, they don't really care. Now the real consequences, we talked again on the last session. Air Canada's chatbot gave a passenger incorrect policy. There was no self check, no loop back, just a confident answer, but it was wrong. And the Canadian tribunal ordered Air Canada to honor the discount their AI invented. And we looked at the fix also, right? The fix was just one extra reasoning step. And Air Canada had to pay a huge amount of money for that in the courtroom. Now look at row 4, the cost. The row everyone ignored, especially the companies who are running out of the AI budget for this year. So this row everyone ignores until the invoice arrives. First one, traditional RAG, it's cheap. Graph, if you look at it, medium, and then of course Agentic being very expensive. So left to right, it's cheap, medium, expensive. Every ounce of extra brain power costs you speed and money. So the industry has now a name for what happens when you ignore this row, and that is called token tsunami, right? We get into a problem of runaway agentic loops, agents trying on errors, reloading full context on every follow-up, spanning, sub-agents, multiplying costs 3 to 7 times before anyone notices. And one e-commerce firm watched infra costs jump from $5,000 a month in prototyping to $50,000 a month in staging. Same system, same questions. A reason? Because nobody had set a retrieval limit. Now, again, there is a stat from IDC which says 92% of business implementing agentic AI experience cost overruns. 71% has no visibility into what was driving them. And I did mention about Gartner March 2026 report in my last session, where agentic models burned 5 to 30 times more tokens per task than a standard chatbot. Now, enterprises discovered their multiplier only after production bill arrived. So here is the gist of the entire slide in one sentence. The escalation ladder. Starting with traditional AI, it is cheap, it is probably enough, and use graph only when your knowledge is kind of genuinely connected. Go to agentic only when the case needs someone to think, use tools, and act on it. Don't don't try to hire an expensive detective for a basic and simple fundamental query. Now, if that escalation ladder just reframed how you think about AI architecture, I would suggest that you hit the like button right now and subscribe to it, because in the next session we are going to build one. Now, for last two slides, I have called this one a smart detective, right? When we talk about the agentic rack. Now that's just a nickname. Now let's actually open up his head and watch him solve one case step by step. Now follow the arrow along with me. Now assuming a case comes in, and what is that? That's basically a user intent, right? It starts at the top. If you look on the screen right now, a question arrives, and the first thing he does is stop and ask, what is this person really asking? And not just the words, the intent. If you get that wrong, everything after it is a wasted time. Now, what he has to work with, look at the left. There are two assets. On the top, you look at the data and knowledge sources, the files. Every document, every record, every data source he can search. Now, just below that, if you look at it, tool connections. Things a detective can actually use or an agent can actually use. What he can look something up for, and then it can run some checks, send a message. As against to that, if you look at the traditional AI, the traditional RAG, he was a beginner. It can only access a file. But a good detective has access to both the knowledge as well as the tools. Now, he looks things up and then he thinks, right? So it retrieves and then it starts thinking. And how does it think? It thinks through an LLM. So if you look here on the screen right now, you retrieve and then it passes it to the LLM. Now, this detective pulls the files that matter, not the whole cabinet, right? And we talked about it in the last session. It brings them to the brain in the middle. And here is the important bit. He doesn't just read, he asks himself, do I have enough to answer or do I need to do something else first? He picks a tool and uses it, reason and select. And then it goes to tool execution. If he needs to act, he picks the right tool, just the one he needs, and it runs it. It gets a result back. Now this is the part a normal chatbot cannot do. A chatbot can only talk, it can only respond to your queries one at a time. But here, this one can act. The part that really matters, I would say, is the agent loop. If you look just below retrieve, you see one agent loop. He stops and he checks his own work. Did that actually answer the question? If yes, he moves on. No, he follows the red dot. Again, goes back and retrieves some more information. Look again, rethink, try again as many times as it takes. Now, that loop is the whole point. A basic system gets one try. This one keeps going until it gets it right. He answers, but safely. And when I mean safely, I mean to say, if you look at the bottom, there are guardrails. Nothing goes out without a safety check. Content is appropriate, yes or no. No private data is leaking. Rules are followed. Is everything logged? If anything goes wrong, we block it. If everything is fine, we let it go through. Smart and careful. And another good part about agentic RAG is that it remembers like a good detective, right? He remembers from his past cases. And that is what is being highlighted here as observability and memory. If you look at the bottom right of the screen right now, the last strip at the bottom. Now, that detective's notebook, every case, every lesson written down, next time he has a little better lead. He has his experience from the past, he has his memory from the past. And he doesn't just solve problems, he gets smarter with every case he handles. And that's the architecture. Now, let's move into the next slide. And this is where our hands on starts. And before I start showing you the code, let's talk about what this use case is. Now, if I tell you, what if the assistant we are about to build could read your website, your PDFs, your live databases, and your meeting notes all at once through the exact same pipeline? One system, four completely different data sources, and zero duplicate code. And that's not a demo trick. It's the same design pattern the biggest companies in the world are shipping right now. And let me show you the four front doors, which kind of land up into the same hallway. Door one, if you see at the extreme left, is the web URLs. And try to imagine, when we talk about this use case, try to imagine how you can implement it. The first one, if you see, you paste a URL or a set of URLs, and that's it. Under the hood, Beautiful Soup scraps the page. It strips the HTML, pulls the visible text, hands back a very clean document object. So for if you're using 3 URLs, every URL will hand you back a document, and there are no downloads, no copy pastes. And you can use that information. You can ask free questions and get all the information from those URLs. In a real world scenario, I would take one example. The Royal Bank of Canada built an internal assistant called Arcane that pulls the right policies from the bank's internal web platforms. So specialists, they find them in a matter of seconds, a quick access. And another use case, if you're trying to build a policy or trying to build a competitive pricing model, you can paste the web URLs of 3 different competitors and ask your agentic system to compare and come back with the recommendations. So this is the first use case where we can scrap through the web URLs, get the right information, and you can do a free text search. Door 2, use case 2, is about the PDF files, the second one if you see on the screen. Now, when you use this option, every page you upload, every document you upload through this UI, it creates one document for every PDF. Every page becomes its own document. Page 1 is document 1, page 47 is document 47, and page number are carried in as metadata. But here is the part that kind of trips almost everyone up, and we'll solve it today live. Streamlit hands you the uploaded file as a raw bytes in memory. Now what we have used is PyPDF loader, which you see a line of code there as well. PyPDF loader needs a file path on disk, and those two doesn't match, right? So what's the fix? We use a temp file pattern. We write the bytes to a temporary file, and then we hand it over to the PyPDF loader, that particular path, which loads the document, and then it deletes the file later on. And look at the beauty, it's just 3 lines. And that's what make PDF loading actually work inside a Streamlit. Now in real world, again one example, this is exactly what Morgan Stanley built with OpenAI. Now the advisors querying a library of 350,000 plus research documents in plain language. Lookup time from 30 minutes, it went down to seconds, and it had 98% adoption among the advisors. And the solution was simple, just PDF chunked and retrieved. Same engine you're going to see and write today. Third use case, accessing a database. In this case, we have taken an example of PostgreSQL. Now, this is where enterprise gets real, a direct connection, and we don't need an ORM or any other framework. You pick the table, you pick the columns, each row becomes one document. And the detail that matters in an enterprise is that we are connecting it in a read-only mode. We don't write, we don't change, we don't touch anything. And I'm sure your DBs will be fine with that. We create replicas, read-only replicas, right? Again, in a real world, a support team turning its live ticket data into something anyone can just ask any questions. How did we resolve this particular incident? What was the RCA? What was the turnaround time? Which team fixed it? So that kind of questions can be asked. This is use case 3, and use case 4 is all about uploading a plain text and simply asking the way you do in any LLM as well. Now we talked about it in the last session, right? That why can't we just upload the document, and how a bigger context window doesn't help. If you have missed that session, I would strongly recommend go back and look at it, because that's not how it works. And we also discuss about the reason why we actually need RAG. So door 4, which is the plain text, maybe you have a 90 minutes meeting transcript which nobody is rewatching. You have a research paper, you have a contract clause. You just paste it and you just type, summarize it, and ask for the key action items or ask for the key points, and it's done. 4 doors, 1 hallway. And let's look at the code in detail then. Now, before we get into the setup, let me just give you the prerequisites. When we create this web RAG assistant, what are the prerequisites? Now, it has 4 components on the right. Now, this is the elegance of a good architecture. Each layer exactly does one job. What we have used for the demo purpose, so that it's easy for you to replicate, we have used Streamlit. This is an interface layer. You will see URL inputs, you will see load and index button, a question box, and you can swap it for React, a Slack bot, or any API as well. But for building fast, we use Streamlit, and we have used Python scripts to working web apps in few minutes. So it's quite easy to replicate and create it. Second, if you look at it, is a web-based loader, right? On the left side, if you see. Now, this is a retrieval layer, especially for the first use case where we are going to use URLs. It hits each URL, fetches the HTML, and the component called Beautiful Soup. It takes out everything, from that particular HTML page. Now, the good part is only meaningful text comes out. The third component, if you see, apart from OpenAI GPT, I won't talk about it. I'm sure every one of you know about it. You need to have an OpenAI key. For me, I'm using OpenAI GPT. There's a reasoning layer, and it gets your questions plus the retrieval chunk. So it does not answer from memory. It synthesizes an answer which is grounded entirely on what you have in your database. Now, ChromaDB, it's a memory layer. It's a vector database. The chunks that get embedded, each one is converted into a vector of its meaning and then stored in the ChromaDB. Ask a question, and the ChromaDB finds the chunks whose meaning is closest. Now, four things. That's all. That's all we need. Now, if you look on the right, these are the prerequisites. Instead of installing all the packages one by one, what I personally prefer is to create requirements.txt file with all the libraries required. And then you need to have an API key. Like I said, I'm using OpenAI API key. Then you need the live URLs to test, and then obviously you need some Python. And I'm using Python 3.10. So with that said, let me quickly go to the demo. If you look at the screen right now, this is the RAG AI assistant. On the left hand side, you see there are four doors that I talked about, right? The first one is URL, then PDF, then database, and then text. Let's start with an URL. So I have used two websites, and let me also open these websites here in the same tab. So I'm using one as CNBC, and let's pick, and this is a website I usually use to check about different LLMs. And it has a list of all the LLMs. It's a good website, I would say. So what we do is, first thing, we use these two websites, and if you look on the left, it says load and index URL. So when I click on this, it start scrapping those two URLs, and once that is scrapped, it will show what it has done. It will create chunks. It will also show you the sources. So there are two sources here. We had two websites, two sources, and we have 42 chunks. And now what you can do is you can start asking any questions. Before I go there and ask question, let's see what's there here in this particular. So this is the latest news. And let's say World Cup sends. Let me ask one question on the World Cup first, okay? Now you can use any number of URLs. Here in this case, what I have configured is 3 URLs, but you can have any number of URLs. So let me ask the first question. I would say any news on World Cup, and then I ask AI. So it says the World Cup has sent prediction market volume soaring up to high, and it comes back with a chunk. So let's look what it has here. So it's a World Cup sends prediction market volume soaring at high records, and it comes back with a chunk from where it has picked up this particular answer, right? Let's ask a question from this particular site. So let's see what we have here. So GPT-3 is a decoder only. So let's ask, find me a decoder only transformer model. So it says GPT-3 is a decoder. So again, if you look at this here, it mentions GPT-3 is the only decoder, only transformer model for this. So it is going back, looking at the relevant site and giving back you that particular answer. And also it comes back with that chunk. So if you see, this is the PDF. Now let's go to option number 2. And let me show you, this is the PDF that I'm going to use. And let's say if I chunk it, it says one source, this is the PDF, and then I will try to find an answer. I'll say tell me about transformer architecture in few lines. Now it is searching this PDF, and to show you this PDF, let me go back to, so this is the PDF. So it's a snippet of the very famous attention is all you need, and from this it has created this summary. All right, so this is the second use case. So you can upload your documents, upload your PDF, anything, and then start asking questions that will give you the relevant answer. Third option is database. So let me show you what I have did for this small POC. So we have this PostgreSQL, and if you look at the UI, I created a simple table of a product. So we have these 4 products and their descriptions right here. And then I connected to my DB, and then when I load these columns, it will start loading. It says PostgreSQL source is 1, this one particular table, we have 4 chunks. And let me ask a question about this, and before that let me show you what the content is here. So it talks about LineGraph Pro, which is an enterprise multi-agent orchestration with state management, ChromaDB, vector database, RAG assistant, Agentic enterprise, multi-agent orchestration suite. Okay, so let's ask a question. Okay, let's say give me tools for multi-agent orchestration. So it comes back with LangGraph Pro Enterprise and Agentic Enterprise, because both of them talk about multi-agent orchestrations here and here, right? So Agentic and LangGraph Pro. So you can access any database. This is a simple UI. Connect to your database and start asking free questions. Last option I would quickly show is a text, where you can put in any free text. And for that, let me show you. I created, there is one eye chart I created. Let me use the same one. So this is the one. And if you have watched the second video, this is the one I created for that Crew multi-agents for the diabetic Arogya application. So it has a daily summary table of the meal, and then it has diet routine and whatnot. So let me just paste this entire content here. I'll select text. I will just put, delete this. I'll put the fresh text. I will then start. It says index 15 chunk. And if you see, it is making maintaining the entire trail, right? So we'll talk about the session maintenance also few minutes. This is what is in press release, ask AI, and it comes back with all the details. Okay, so you have 4 options. You have ways to give your URLs, graph from them, PDF, database, text. And what we'll do next is we'll get into the deep dive around the code. So if you see, first thing I would like to show you is how to build this particular application. So let me open my VS Code. And for simplicity's sake, what I'll do is I'll just switch. I'll start from scratch. Let me say session 4, new folder, demo for rack. I'll select this folder. It will switch the workspace. And while it does that, let me show you the requirements.txt file. So this is the default screen you get once you open the VS Code. I'll close this. You have to go and open your terminal and let it open. So by the time it is getting ready, let me try to show you the requirements.txt. Okay, so the terminal is ready. The first thing that we do is we create an environment. So because I said, like I said, I'm using LangGraph and Python. First thing you need to do is you need to set up your environment. So let me just, so to set up an environment, you have to use this command python -m vnv. It will create a Python environment. Once it does that, you will start seeing a folder here. Meanwhile, let me show you the requirements.txt. So if you look at the requirements.txt, we have a bunch of packages here, right? That we have to install before we even start running our code. So let's see. Yeah, so we have still running. Okay, let me then show you what we have in requirements.txt. Okay, so these are the different libraries. So let's talk about these libraries. So we have imported Streamlit, which is a user interface, and it lets us turn a Python script into an interactive web app. So users can ask questions the way you see in the demo, right? That has a very user-friendly UI, right? So you can ask any questions in the browser and see the answers right away. So for that, we have to use Streamlit. And before we go here, okay, so here it's giving me the same problem. So once you install this, if you go inside scripts, you will see activate.ps1. So you have your environment ready, but you need to activate your environment first. So for activating the environment, I'll give you another command, and all these commands and all these tips are there in the link, description link of this video, so you can always go. So this is the command that you need to use to activate your particular Python environment. So when you hit enter, if you see the green, this means that you have activated your environment. So this is the basic simple step. And just to make sure that which folder you are in, what is the location here, if you see you are having this venv. So what you do, you go inside your virtual environment, and then the next very easy step is you bring in your requirements.txt. So what I will do here is, if you see there is a requirement.txt file here, I'll use the same one, and I will try to drag and drop it in my VS Code. So once you have the requirements.txt, you simply pip install this particular requirement.txt. What it will do is it will install all the dependencies here. So if you look, pip install -r requirements.txt, it start installing those dependencies. So while but it says could not open requirements.txt. Oh my god, that is a spelling mistake. So let me rerun it. So if you see, it has started installing all those dependencies. So while it does that, let's go back to the slide where we are talking about all these different libraries. So we talked about Streamlit. LangChain is something that we are using here, and again we'll be using LangChain and LangGraph for a lot of our Agentic AI hands-on sessions. Now this is the orchestration framework. It connects the main piece of your RAG workflow, including whatever documents we are loading, whatever retrieval we are doing, whatever prompt handling we are doing. So LangChain is that framework that helps us in developing all that stuff. Now LangChain OpenAI connects LangChain to our OpenAI models. Like we use it for generating responses, and depending upon the setup, even for embeddings in some cases. Now, LangChain community adds extra integrations from the broader LangChain ecosystem. It gives us access to community supported tools and loaders and that are not part of the core package. So we also need to include the community package here. Now, LangChain Chroma is a LangChain integration for Chroma. We are using it allows LangChain to store and query embeddings from our Chroma vector database, right? Which is the next item here in the list. If you see the Chroma DB, now this is the vector database itself. It stores text embeddings and helps the agent find the most relevant chunk when a user is asking a question. Now, PyPDF, this is an interesting one because this is the second use case where we're using PDFs, right? So PyPDF is used to read PDF files. It extracts text from PDFs, so they can be split into chunks and then indexed for retrieval. Right? In this case, where we uploaded a PDF and start asking questions, the same thing that is enabled through PyPDF. Now there is another library which we have to use for connecting to our PostgreSQL. This is the next one, PyPsychoPG2 binary. So if you want to store metadata, logs, or any conversational history in database, this is a package that handles all that stuff. Now there is a Python.NET environment that helps us in loading the environment variable. So that is the next one. Beautiful Soap 4 is, I think I mentioned earlier, it's used to parse the HTML content, and it helps in extracting that readable text from the web pages. So when we want to ingest any online resources into the RAG pipeline, this is what we use. So overall, these packages cover the full flow: data ingestion, embedding, and retrieval. It also includes model response generation, storage, and the web interface. And let's quickly see where we are with the installation here. Okay, so it's still running. So once it runs, we'll come back here. By the time, let's talk about the next slide. So here, if you see, I tried creating a small slide that explains the code here. Okay, and we talked about the two pipelines in the last session, right? The pipeline one, where you are trying to set up your vector database and all that stuff, and then we had pipeline 2, the retrieval one, right? So let's try to go a little bit deeper into the code. Now phase 1, which is the indexing, right? This is what happens the moment a user loads the URL, the first demo that we see, right? Now think of this phase as the agent doing its homework. We are reading everything, organizing it, filing it away, saving it in the vector database. So when the question comes in, we are ready to answer that question in milliseconds. Now it has 5 steps. If you look on the screen right now, the first step is where the user enters the URL. In our case, we used only 2 URLs. One was the CNBC one. Now we have those text boxes on the sidebar, right? We have one button called load and index. So when we click on load and index, that is when it is trying to extract the information and loading it into a vector database. Now there is a simple 4 line of codes here, right? It takes the first, second, and third URL. In our case, we took only 2 URLs. Now scrapping happens only once when you click the button, not once per question. Not every time you are asking question, it's not going in scrapping it. So it happens one time, it builds a vector database, and then once you ask a question, it answers it. So the agent reads the page now, stores what it learned, and then it works from that snapshot for the whole session. And we have seen how caching works also, right? It's faster, it's cheaper, it is consistent. Now step 3 is splitting into chunks. Now this recursive character text splitter, it cuts each document into 1000 character chunks with 100 character overlap between neighbors, right? And why this overlap, I'm not going to explain it in this session. We had a very detailed session last week. So I would say, if you're not clear about it, pause this video, go back to the last session. Long story short, we use overlap because we don't want any sentences ever to fall into the gaps between two chunks. We call it a boundary problem. We discussed last time, right? So if you missed the boundary problem, that's session 3. You have to go and watch them. Step number 4 is embed and store. So every chunk goes through the OpenAI embedding in this case, becoming a vector of that 1536 dimensions that we talked about in the last session, which encodes its meaning, not the strings. Now those vectors land in ChromaDB. Then we built a retriever configured to kind of return top 6, the k value which we talked about in the last session, which are the most relevant chunks, right? And then step 5, we save to session state. Now here is a trap. Streamlit reruns your entire script on every interaction. Without session state, every question would rescrap, rechunk, or re-embed. So that's the fix that we have done here. Now it has 3 lines, pretty straightforward, pretty simple, st.session state retriever LLM prompt, and the expensive work runs once per session, not once per question. So the homework is done, the agent is ready. Let's see where we are with this. Okay. So sometimes what happens, it takes a lot of time. Now for that, let me try one more thing. So it says pip upgrade. All right, we'll do that. It is asking me to update the version, so let's do that. Let it run, and once it upgrades, then we'll go back and again run the requirements.txt. So let's wait for a second, and then between that, let's go back to the slides. Okay, so we talked about the first pipeline. Now let's talk about the second one. Now this is where all the preparation pays off. Now user asks a question. So you have a vector DB ready with all the information that we wanted us to save in the vector database. Now step 6 is user asking a question. Now it's a text box, a button, ask AI, 2 lines of code. If you look at it, this is how we create that. That if you want to look at the UI one more time, let me quickly show you that. So here we have this ask a question and then ask AI, right? Where we ask the questions. So you can ask anything the way we did for each of the 4 different cases. Step number 7 is retrieving the top 6 chunks. So it's simple 1 line retriever.invoke query. Under the hood, the question becomes a vector, and we use the same embedding. And again, we covered this in previous sessions. ChromaDB computes cosine similarity between those questions, the question vector, and every chunk vector in the database. And because we have configured k value as 6, the top 6 score wins. Now step 8, building the context string. 1 line that's easy to overlook and critical to get right. Now if you join all the 6 chunks into one string separated by, let's say, double new line, so the model can see where each chunks end. Think of it as assembling the briefing document, 6 paragraphs of evidence, and you are about to hand it to the world's most capable analyst with one rule: answer only from what is in this briefing. So that is the step where you are building that context string. Next step is formatting the prompt. The template combines the question and the context with the guardrail instruction baked in. Now use only the provided context, don't speculate. That is the key message here. Step 10, generate the grounded answer. LLM.invoke message. The model reads the briefing, reasons across the evidence, synthesizes the answer, and then it comes back with the answer. So this is the bit we wanted to cover for the retrieval section. Now let's see where we are with this. Okay, so your upgrade is done. I will try to run my pip install again. Now while it does that, let me also try to bring back, I'll try to show you this file as well. So let's go here. Let me show you the actual Python file now. So this is just the preparation we are doing now. Look, if you look at this Python file, now this is just one single file that you need to run. Now let me try to explain this file to you. So if you look at the screen right now, the first one says import OS. Now this provides access to your environment variables via os.getenv, which we'll see towards the later end of this file. Now this is used to read your OpenAI key, right? Because we don't want our OpenAI keys to be exposed or embedded in the code. So we use this OpenAI key environment variable, right? And next one, if you see, is import temp file. This temp file is exclusively used for our second use case for PDF handler, right? When a user uploads a PDF through a Streamlit file uploader, the file arrives as an in-memory bytes. Now this is where this temp file concept comes into picture, which I explained earlier, right? Now if we talk about environment variables, so this is the .env import load_.env. Now this load_.env reads the .env file where we have your OpenAI key and rest of your configurations. Next one, if you look at it, is the Streamlit import Streamlit as ST. This is the Streamlit is the entire web framework. It converts your Python scripts into interactive web applications without even requiring any HTML or JavaScript or any separate web server. Every UI element, text input, buttons, tabs, everything you can handle with Streamlit. Next one, if you see, is the LangChain document loader. Now I would talk about two here because these were the two we were using. The first is the web-based loader. You see the import web-based loader and PyPDF loader. Now web-based loader accepts a list of URLs, fetches each page using the request library, and then it parses the HTML and kind of scraps everything from that web page. Similar case is for the PyPDF loader also. It accepts a file path to a PDF, extract text page, kind of page by page using the PyPDF, and returns one document per page. Now each document's metadata is also kind of captured, like I was explaining earlier. Next one is, if you look at the next line, from LangChain_text splitter. Now recursive character text splitter is the most production reliable chunking strategy. At least that is what I have learned. It tries to split text at natural boundaries in order. Paragraph breaks, double new line, then single new line, and then sentences, and finally at a arbitrary character position as a last resort. So the boundary problem rarely happens, and even if it happens, we know that we have another solution for that, which is called our chunk overlap, right? Okay, now let's talk about Chroma. This is the vector store, right? From LangChain Chroma, import Chroma. So Chroma is an open source embedded vector database. In this application, it runs entirely in memory. So no server is required, no persistence layer between screens. So this is again a very effective way of quickly running and bringing up your workspace. Now, next one is your LangChain OpenAI, which is nothing for your OpenAI integrations. It does two things. One is for OpenAI embeddings, which wraps the OpenAI embedding API, and it is called once per chunk during the indexing to convert the text into that 1536 dimensional vector. The second one is chat OpenAI, which wraps the OpenAI chat completion API. Now you can configure, and we'll show you towards later part of the session. You can configure the model whether you're using GPT-4 or any other model for that matter. You can also set a temperature of your choice, low randomness for factual answers, or you want a lot of imagination or high randomness, then you can configure that. You can also configure max tokens using the same configuration. Next one is LangChain and core prompts, which imports the chat prompt template. Now this prompt template helps in assembling the final prompt that is sent to the LLM. And in this app, it creates a two-message conversation, a system message that instructs the model to answer only from the provided context, and then a human message, which basically you are asking, as a question or a query. Now let's talk about document class. Now document class is kind of a LangChain's universal container for a piece of text. It has a page context and it has a metadata. Now, what it means simply is that you're capturing the context, the actual content of any page, and also capturing the metadata, whether it's in page 3, page 10, page 12. That helps in later on, identifying that what is the actual source of that particular information. Now let's scroll down a little bit. Now this is the page config, right? This is a Streamlit page config, and I'm not going to cover the HTML part of it. You can use any tool, any LLM, any chat GPT, anything, or I personally use Claude. It gives you a very beautiful UI, and you need not even go into that. So I'll not cover the UI part, but let me still cover the page config. Now set page config must be the first Streamlit call in any script. Now it sets the browser tab title. If you see here, RAG Assistant, and icons and switches Streamlit to white layout. And it's a simple best practice that we can follow at least. Now let me go down a little bit, and I will show you the next section of code which is kind of relevant. This is all your HTML and CSS and all that stuff. You need not. Now, yeah, session state. Now, session state is important because now I think I told you earlier about it. Streamlit reruns the entire Python script from top to bottom on every user interaction, every button click, every keystroke. Now, without you maintaining a session state explicitly, every variable would reset to its default value on each rerun. So this is what it does. Now, if you look at the different parameters here, I'll not cover everything. I'll cover just the key ones. Retriever. This is the ChromaDB retriever object returned by build vector store, and we'll talk about build vector store. Now, this is the one which is helping us in retrieving the right chunks, right? Then second one is LLM, the chatbot, the OpenAI LLM object that we use. Then we have the prompt, then we have index sources, the count of document, the source type, whether it's a URL, it's a PDF, or it's a text, or it is from your PostgreSQL. It also has a configuration type for chat history, and then obviously your API key. Now here it's just a placeholder. We are not going to show API key here, or we are not going to put the API key in the code. So this is now let me take you to one important. We are almost towards the end of the code here. This is build vector store. Now this is one important function or important piece of code, and you did not learn it or cram it. If you look at here, the recursive character text splitter, chunk size 1000, chunk overlap 150, right? This is what we discussed earlier. Now step one is chunking, right? Now this recursive character text splitter, it splits every document in docs into smaller chunks, and those are up to 1000 characters, and we are having 150 characters overlap. Now the result of this is a new list of document objects, and which is one per chunk, and eventually every chunk is going to get converted into a vector, right? Now step two is embedding and storing. Now if you look at this chroma from documents, where it is, yes, it takes document equal to chunks, embeddings equal to OpenAI embeddings, and which whatever API key we have used, right? And what it does is it iterates over every chunk, calls OpenAI embedding API to convert each chunk into that vector. The vector is nothing that 1536 dimensional float vector that we have talked about so many times. Third step is retriever configuration, vs dot as underscore retriever. Now what it does, it wraps the chroma collection in LangChain's retriever interface. And while it does that, you have to look at the parameters which are being sent. Search type similarity, and you are also setting the k value to 6. I'm sure everybody knows now from the last few sessions what does search type similarity means and what does k equals to 6 mean. So here is the one. So this build a vector store is a very important, I would say, method that we have created here. Last is a return value. It returns a tuple, which is the retriever, and a chunk count. The chunk count is stored in session state, and it displays in the stat strip, like you were seeing. The source is 1, the chunks are 40, 42. So that all that value is populated based on here. Now one last thing is build LLM and prompt. Now, this is the piece of code. This function basically creates the LLM and the prompt template. Now, both are kind of recreated every time a new source is indexed. Now, chat OpenAI, if you look at the line number 364, LLM equal to chat OpenAI, this initializes the GPT-4o chat model and it sets the temperature to 0.3, which keeps the answers factual and deterministic. Max token size that we have set up is 600. Now the API key is passed explicitly, so the model uses exactly the key in the session state, not as a global environment. And then you can choose to configure it the other way as well. The second one is row number 366. Prompt is equal to chat prompt template. Now the system message contains the instruction use only the provided context to answer. Now this is a critical grounding instruction that prevents the LLM from drawing on its own training data instead of the index document. So that's another important configuration here. Now, meanwhile, let me take a pause. Let me go back to the terminal here and see where we are. So if you see inside this V and B, we have your requirements.txt. In the same root, you need to bring your Python file. And then because it's a Streamlit piece of code, the way you run it is by writing Streamlit, then you run, and then your whatever the py file it is. Okay, let's try to run this and see what happens. Okay, so it has run and then it gives you a link. Let me copy it and let me try to hit this. So here it is. Now you see this is the fresh instance that we created. You don't have anything pre-populated or anything, right? So this is still loading, and by the time it is loading, let me see. Now it has loaded the full page. So here you can put in your OpenAI key. Not recommended, but for simplicity's sake, I have put it here. You have the URL, PDF, DB text option. You ask the questions and whatnot. This is how it works. And let me also go back and show you the one which I was running in the beginning. So what we created from here, I'll just quickly summarize. First thing, you create your environment, you put in your requirements.txt file, you run the requirement.txt, have all your requirements in place, then you use your app.py. Now what we did, let me quickly summarize. So we built the assistant. The retrieval works, the reasoning kind of is sharp, we were able to get the answers and the answers look perfect. But this is very fundamental, this is a very basic setup that we did and very basic RAG agent we created. Now but nobody is showing you uh, the real pain, what it goes behind when such solutions go into a production environment. Now in a live enterprise environment, that same assistant, you know quietly exposes a customer's social security number or some PII data in a response, or it hits a runaway loop, burns let's say $15,000 in inference cost overnight. Now what is inference cost, I'll explain in the next session. Now, or maybe a regulator asks you to show the decision trail and you have nothing, right? Now this is not a retrieval problem, this is not a model problem, that is a missing foundation problem. And it is exactly why 40% of agentic AI projects will be cancelled before 2027. This is nothing from my side, this is the Gartner's report. Not bad models, not bad retrieval. Teams build the existing layer and script the infra that masks it safe to let the agents act at scale. So, two layers, I would say, neither glamorous but both non negotiable. And that is exactly what we are going to discuss and build in the next session. Now, here on the screen right now, look at the 5 gates. Now, gate 1 is your content filter, not about just the bad words or swear words. This is about prompt injection, the most dangerous attack vector nobody talks about. Your agent retrieves a web page, and what happens hidden inside, maybe in a white text on a on a white background, and there is an instruction saying that ignore all previous rules and do something else. Now the agent reads that page, and in this case, we saw that our agent was reading a page, right? But when these kind of attacks happen, the page is itself reading the agent. And I'll explain it in detail in the next session. Now, gate 1 is a lock on that front door. Now, gate 2, the PII and secrets detector. Your vector store contains everything ever indexed. Now, support transcripts with customer names, HR, wikis, salaries, maybe SSNs or onboarding docs with API keys and whatnot. One exposed record is not a technical incident; it's a regulatory breach. No one is going to give you a you know favor that it was just one instance, one of no. So gate 2 redacts it before the model ever reads it. Third is policy check. An agent that answers questions is manageable. An agent that takes actions is a different category of problem. Can it send an email, delete a record, maybe initiate a payment? So gate 3 is an agent's job description written in code. A junior employee has no signing authority on a 50K purchase order. And in the same way, your agent shouldn't either. Gate 4, rate limiter. The gate on zero architecture diagrams until the invoice arrives. Now, one runaway loop, no with no stopping condition, and $15,000 in under 10 minutes. And this is all documented. This is all real. And like I said earlier, this is what industry is calling token tsunami. Now, if you do some tweaks, just two configuration parameters, teams can help in avoiding those tsunamis. And we'll talk about it in the next session. Gate 5 is the audit log, and this is kind of unglamorous one, I would say, the one that saves you in the regulator's room. Every query, every retrieval, every tool call, maybe every response, time stamped, immutable. Your GDPR, HIPAA compliance, everything, all those questions. Anyone asking, show me why your system made that decision. If you don't have this gate 5, you will not be able to answer. Now, some real example, DoorDash's LLM guardrail evaluates every response before it reaches a dasher. Now, add all that with the layer 2, if you see on the bottom of the screen right now. Observability and memory. Conversation history, memory store, metrics and traces, feedback loops. And we are going to talk about all that good stuff in the next session. Now, here is the truth nobody says out loud in the demo video. An AI system that cannot be trusted, cannot be deployed, and should not be deployed. And an AI system that cannot be deployed cannot change anything. The guardrails are not the constraint, they are the foundations. And next sessions are going to be around these guardrails and observability. And we focus and we deep dive into all these topics. Now, before you go, three things. One, subscribe. Next session, we build this entire guardrail layer living in Python. Every gate firing in sequence. Miss it, and the architecture will not click. Second, drop a comment. Which gate is your current AI system missing? Three, share this with one person making AI decisions right now. And I'll see you in session 5. Stay curious, stay disciplined, keep building.